So now let's try an example where we use the rate law we determined in the previous video to actually calculate the rate at different time points in the reaction. So this can be applied to any rate law problem really, because if you know the expression for the rate law, including the reaction orders, and you know the value of the rate constant K, which you can calculate from the experimental data once you know the rate law, if you know the rates. If you know all of these things, you can calculate the rate at any time point in the reaction. So let's take the reaction that we used in the previous video as our example. The reaction where two nitrogen monoxides react with bromine to make two NOBRs. For that reaction, we determined that the rate law is rate is equal to the rate constant times NO squared times bromine concentration. So it's second order in NO and first order in bromine. And we also determined that the rate constant was 1.2 times 10 to the 4 liters squared per mole squared second. So I suggest that you go back to the previous lecture video and watch that one again so you know how we determined that rate law and how we calculated that rate constant. Now, we have all this information. So let's say that we start this reaction with 0.1 molar each of the two reactants. So 0.1 molar of NO and 0.1 molar of bromine. Let's calculate the rate at two time points in the reaction. Let's calculate the rate right at the start of the reaction. And let's calculate the rate after 0.02 moles per liter of bromine have been consumed. So we can do this because we have all the data that we need to do this from the rate law and the rate constant. Let's make a list of the species that we have. So we have two reactants here. The first reactant that we have is bromine, and the second reactant that we have is NO. We have the initial concentrations of 0.1 molar of each of them. So the initial concentrations are going to be 0.10 molar for each of them. Okay, well, I think that's probably enough to figure out the rate at the start of the reaction anyway, because we know what the rate is, and we know what the value of K is. So it comes down to plugging in the numbers. The rate is equal to the rate constant K times the concentration of NO squared times the concentration of bromine. We know the rate constant is 1.2 times 10 to the 4 liter squared mole squared seconds. And we know that the concentration of NO at the beginning is 0.10 molar. I'm going to write molar here as moles per liter, and I have to square it because of this 2 here. I have to square it. And we know that the concentration of bromine at the beginning of the reaction is also 0.1 molar. All right, so now I can do the math. Okay, I have 0.1 squared, so it's 0.01 times 0.1 is 0.001 times 1.2 times 10 to the 4th. Well, that should come out to 12. Now the units are going to be, okay, so we're going to cancel out the squared units of molarity with here. You can cancel out the square here too. And I'm going to be left with units of moles per liter per second, which is exactly what I want, moles per liter second. That's what a rate, those are the units of what the rate should be. And this happens because the units of K vary according to the reaction order. So we want the rate to always be in units of molarity per second. So this is the rate at the start of the reaction. We also want to figure out what the rate is after 0.02 moles per liter of bromine have been consumed in the reaction. So we started out with 0.1 molar concentration. Let's figure out what the change is and what the new concentration is after the consumption of 0.02 moles per liter of bromine. So we're losing 0.02 molar of bromine. And now I need to look at the stoichiometry of the reaction. So let's look at that here. Because I can see that for every 1 mole of bromine that gets consumed, I'm going to be consuming 2 moles of NO. So that means that I have to double the consumption of the NO with respect to bromine, okay? So this is because there are 2 moles of NO consumed for every 1 mole of bromine that gets consumed. So the new concentrations are going to be, looks like 0.1 minus 0.02, so that's 0.08 molar for bromine and 0.06 molar for NO. Because there's 2 NOs for every mole of Br2 that get consumed. So now I have new data to plug into the rate equation. So this was at the start. Now let's calculate the rate for the point of time when I've already had the reaction going for a little while. So the rate constant is still 1.2 times 10 to the fourth liters squared per mole squared second. The rate constant doesn't change. The rate itself, however, does change. So my concentration of NO is 0.06. So 0.06 moles per liter squared. And I am going to, here, I don't want to be confusing, so I'm just going to take out that time sign. And then I have 0.08 moles per liter for the bromine. So if I do that arithmetic, I have 3.5 moles per liter per second as my rate. Okay, so this is a big contrast, right? At the start of the reaction, the rate was 12 moles per liter seconds. So this is the rate at the beginning. And this 3.5 mole per liter second is the new rate. So this really should hit home in terms of what we talked about at the very beginning of this chapter. The rate at the beginning is really fast, but then the rate slows down as the reaction progresses. So you can see here how the reaction rate has decreased really substantially from the start of this experiment. It started out at 12 moles per liter second, and after only 0.02 moles per liter of the bromine gets consumed, it already has dropped to 3.5 moles per liter second. So you can see that there is a dramatic reduction in the reaction rate. So when you're doing these problems, remember, K is the rate constant. So K is constant throughout, but the rate itself is going to vary over the course of the reaction. The rate starts out high, and then as time goes on, the rate decreases as the reactant gets consumed.